In this slide, or in this series of slides, we're going to talk about pre-processing the EEG. And when we pre-process the EEG, we mainly are talking about two things. We're talking about some filtering, and we're talking about the identification of artifacts, and hopefully the removal of some of these artifacts. So if we look at some pre-processing steps, and I will just mention here that there are some excellent lectures on the EEG lab site on pre-processing and processing pipelines, which is how people refer to this, and we will refer you to those as part of the class. But basically, the pre-processing steps, after you acquire the EEG, there are some pre-processing steps that are required. A lot of the systems have software that do a number of these steps, some don't. Some do, and people choose to do their own because you have a little more control over how it's done. But usually you export to MATLAB, EEG Lab, or some other third-party software. In the case of EEG Lab, it's designed to read directly files that come out of the most common EEG hardware systems. And both of the systems in my lab are supported by EEG Lab. You can read files directly in. So the first thing to consider is noise. Noise is different from artifacts. It usually comes from sources outside of the body. And the most common noise issue is 60 hertz noise, just coming from surrounding electrical equipment, as well as the harmonics of 60 hertz. There's some thermal transducer noise, other sources of noise, fluorescent lighting. Some of these electrodes too are so sensitive that if there is a lot of external motion, like you're passing your hands near the person, that can be picked up. Usually noise can be effectively filtered, so we can often, before the signal is analyzed at all, we use a 0.5 to 50 hertz filter, because usually we're not analyzing higher frequency gamma. If we are analyzing higher frequency gamma, we use a 0.5 to 100 hertz filter, and then we use a 60 hertz notch filter. That will take care of most significant sources of noise from outside the body. So typically EEG is filtered from 0.5 to 50 hertz. This is usually using a bandpass filter. Once again, if you're analyzing gamma, you have a little different approach. Most good EEG systems have a built-in 60 hertz notch filter. Sometimes this works well and sometimes it doesn't. So we've had some issues in our lab with 60 hertz filter, just really not effectively filtering out 60 hertz. Brain-computer interface systems are a little different animal. A lot of times the guys that do brain-computer interface are interested in a very narrow band, often the band from 10 to 12 or 8 to 12 hertz. In their case, they'll implement a much narrower bandpass filter. It gives them then a lot less data to have to deal with, and a lot less processing to do on the other end. One thing to note is if you're using EEG Lab with the most current form of EEG Lab and the most current version of MATLAB, for whatever reason the linear bandpass filter doesn't work. I don't know why. It's either a glitch in the code or it's a glitch in the current edition of MATLAB, or both, and how they communicate. So to bandpass, you have to run a low pass filter first and then a high pass filter if you're using the linear option. If you use the nonlinear option, it's not a problem. Okay, well, so that was for getting rid of noise. Getting rid of artifacts is a different animal. So when you have artifacts, there really are two steps. One is to identify the artifacts, and the other is to remove the artifacts. And either and both of these steps can be done either manually and or automatically. So we'll talk a little bit about that. First, it's useful to look at the types of artifacts, and there are 4 common types in the EEG. The first is a muscle artifact. This is usually an EMG, electromyography signal. It's usually due to movement of the face or the neck. Jaw clenching is the classic really bad muscle artifact. You can move your hands to some extent, and that'll have a minor a very minor effect on the EEG on most systems. The next artifact that's significant are eye movements, and by this I just mean you're moving your eyes around either vertically or horizontally, so you're basically shifting your gauge. There are eye movement monitors. They're basically the same as EEG electrodes. They just go at the top and bottom of the eye and on either side of the eye, referred to as VEOG and HEOG, standing for vertical electrooculogram and horizontal electrooculogram. Sometimes if you measure those separately, then you have a baseline signal that can be subtracted out for artifact removal algorithms. Blinks would be the third type. This is a type of muscle artifact, but as you'll see, it actually looks quite a bit different than the muscle artifact due to EMG. People do blink their eyes a lot. This shows up as a very large artifact on most EEG. And then finally EKG, which is electrocardiogram, sometimes gets superimposed on the EEG. You tend to find this very subject to subject. It's a lot worse for some subjects than for others, and I don't know why. Maybe some people have a stronger pulse in their head. Maybe it has to do with hair. I don't really know. I just know that we see this with some subjects. We see this a lot. With other subjects, we don't see it at all. So here are just some pictures of what typical EEG looks like. In this example, we're seeing a lot of muscle artifact here. Over here on the right side of the figure would be a more normal looking EEG. But all of this kind of just noisy looking high amplitude stuff is muscle artifact. Here's an example of an eye movement. You can see here in the background normal EEG, and then you almost see these plateau-like steps, and then EEG continues stepping down, EEG continues stepping up, EEG continues. So these lower frequency, almost square wave looking kinds of things, those are vertical and horizontal eye movements. This is an example of some eye blinks. You can see they're quite different in nature, both from eye movements and from the EMG. You can see that for some probes, the signal has a different polarity than for others, and it also has a different amplitude. And so where your probe is located depends on how bad this artifact is. And then this is an example of an EKG artifact. Also, kind of some of the same thing we saw before, that there are some channels where this hardly shows up at all. There are other channels where it shows up pretty significantly. You can see this one is pretty repetitive. It has a fairly high amplitude. So if we think about what all of these artifacts have in common, and we can kind of page back and let you have another look. The one thing that they all have in common is that they are significantly higher amplitude than the background EEG. Some of them, like the EKG, are fairly temporally repeatable, almost cyclical. Some of them, like the eye blinks, tend to have a fairly repetitive shape. So you can see that the shape of the artifact, at least within a channel, is fairly repetitive. The eye movements, that's a little more difficult, although there's a little bit of repetitive kind of shape there too. The muscle artifact is just basically looks a lot like high amplitude noise. So how do we remove these artifacts? Well, the problem is that artifacts share bandwidth with the EEG, so we can't really filter them out using traditional methods. So the first approach is to just use a manual identification, manual removal approach. Here the user looks at the data, identifies artifact-free regions, throws out everything else. This really is still the most reliable method. The problem is that sometimes you have so many artifacts, you're literally throwing all your data away. So the next approach is to have automatic identification and marking of artifacts, and the user makes a decision on whether to reject. So in this case, the system makes a decision on what's an artifact, usually based on thresholding of the amplitude. So we look for sections of the signal that exceed a user identified threshold. Then the system identifies the artifacts and prompts the user, do you want to discard or not? So because of that, it doesn't really save a lot of time. It does move the decision of whether something's an artifact or not away from the user. That can be a good thing. It can be a not so good thing, depending on your perspective. Rejection means literally the segment of data that contains the artifact is physically removed and not analyzed. So in addition to systems automatically identifying, there are some systems that will also automatically reject without any user input. So literally this means the signal is actually physically removed. The problem with this is a couple of things. First of all, if you've got data that you're acquiring and you're acquiring it in a consistent way and you want your sample length from across your trials to be the same, if you start randomly throwing away segments of data, suddenly you've interfered with your timing. The other issue is if you just randomly pull out a segment of data, you're attaching two segments of data that are not adjacent. And so you can have these step function type shifts between points, which creates problems with your frequency analysis. So removal or rejection of artifacts through just removal of the segment that has the artifact in it carries some issues.